All right, I'm really excited about class today. I think it's going to be a fun day. There's something called the logistic map. I like writing it as f sub mu of x equals mu times x times 1 minus x, which of course you could also expand out to be mu x minus mu x squared. Okay. We're interested in thinking about this when mu is positive. And if you think about the graph of this, in the case where mu is positive, you can see the x-intercepts by the factored form are going to have to be at 0 and 1. And because negative mu is in front of x squared, the graph is going to be an upside down parabola. It's going to have to look like this in general when mu is positive, something about like that. I'm not saying what mu is, so I'm not saying how high it goes. Though the maximum would occur at 1/2, it's got to be halfway between the x-intercepts. We're interested in iterating this function. In other words, we're interested in defining a sequence recursively. Start with a seed. In other words, an initial value, call it p sub 0, and use this recursive equation, Pn equals f of Pn minus 1, f sub mu, I should say, of Pn minus 1, to generate a sequence P0, then P1, then P2, then P3, etc. Starting with the subscript of 0, but I don't have to start with the subscript of 0. It's just convenient here to emphasize that P sub 0 is like the initial condition. But you could start with P1 and say that's your seed, your initial condition, if you like. Yeah, that would be a different name for this, is initial condition. Not talking about applications, but maybe we will next Tuesday. You can apply this to some population models, for example, discrete population models, as opposed to continuous population models, which would come from differential equations. And in fact, sometimes this is called a difference equation, even though you don't see a difference in it. You could subtract this from both sides and then think of it as a difference. Yeah, sometimes these recursive equations are called difference equations, which you could also call diffie-qs, just like differential equations are diffie-qs. But of course, that would be a little confusing, though they are related to each other amazingly. Anyway, with your calculator, what I'd like you to do is I'd like you to think about this in the case, we'll think about this together, and then I'll have you do one separately. Think about this in the case where mu is 2.8. So we're going to be thinking about f sub 2.8 of x, which will be 2.8x times 1 minus x. And let's pick the seed to be, say, 0.1. Guess we're going to do this all together here. So when your calculator, just plug in 0.1, hit enter. And then to iterate this function conveniently on this kind of calculator, type 2.8 times the previous answer key is above, again, the negative sign down here, ANS. So do second ANS times 1 minus ANS in parentheses. Before you hit enter, let's estimate what this is going to be. So we'd be doing 2.8 times 0.1 times 0.9. 2.8 times 0.1 would be 0.28 times 0.9 is going to be in the ballpark of 0.24 or 0.25 or so. 252. Then if you just keep hitting enter, it plugs that number into F over and over and over again. 0.252 being plugged into F gives you, hit enter, 0.5277888. Hit enter again to plug that number into F. Get 0.69783777913. Keep hitting enter. And what do we observe? We see a sequence. P1, we started with P0, P1, P2, P3, P4, etc. That is bouncing back and forth. It's not monotone. It's bouncing back and forth. But look at these numbers. They are getting closer and closer together. I don't know, we're up to around 10 iterations now. Keep going, we could count them. It does look like these numbers are converging to somewhere about 0.643. Yeah, to 3 decimal places, it would round to 0.643. So it's converging, but kind of slowly, more slowly than you might hope for. Converging to what? Well, yeah, about 0.643, but what would it mean in terms of this function? We're iterating a function like we talked about on Tuesday. Function iteration, what would it be converging to? It's not converging to a root, right? Those are 0 and 1. It's converging to a fixed point, a number that when you plug in, you get the same number back. What's this line supposed to be? Y equals X. Where does this function equal itself? Where does the input equal the output? Well, 0 is 1. It's converging evidently to this other one. This must be the 0.643. 0.643 when mu is 2.8 at least. When mu is not 2.8, it's probably something different, right? That would make sense because the graph would change. About 0.643, it seems, when mu is 2.8. That's your fixed point. Let's see if we can solve for it algebraically in the general case. So if I set f sub mu of x equal to x, can I solve that equation? Sure, it's going to be a quadratic. There's f sub mu of x. Subtract x from both sides. You don't even have to use the quadratic formula. If I subtract x from both sides and factor out the x from the two terms mu x and minus x, I'll get in parentheses mu minus 1 times x. You don't even have to use the quadratic formula here. You can factor out an x. Like that. And certainly one fixed point is x equals 0, and the other fixed point is when the thing inside the parentheses is 0, which is going to occur when x is mu minus 1 over mu. Which, if mu is 2.8, is going to give you 1.8 over 2.8, 18 over 28, which would be 9/14. When mu is 2.8, 9/14. Yep, about 0.643. That's what that sequence is converging to. What happens if I change mu? Let's let, in our next example, mu be 3.4. So we're thinking about iterating f sub 3.4 of x, 3.4 times x times 1 minus x. Start with p0 to be 0.1 again. The p0 is kind of irrelevant, actually. Different p0s will produce different sequences, but they still converge to the same thing, at least in the first example. I mean, it is still related. If it was an application, it is still related to the initial condition. And again, different p0s will produce different sequences, but at least with the first example, they converge to the same thing, 9/14. I hope that's believable based on just continuing to hit enter here. Though the p0 does have to be between 0 and 1. I should add that. Well, what about this case? Let's try it together. So hit a 0.1 again. Now type 3.4 times the previous answer times 1 minus the previous answer. Whoops, where in the world? I don't know how I got to that screen. Okay, do that again. White 1, okay. 3.4 times previous answer times 1 minus the previous answer. 3.4 now, not 2.8. P0 is 0.1, P1 is 0.306. P2 is 0.722. P3 is 0.682 approximately. Keep going. We're bouncing back and forth again. But now the numbers are not getting closer together. Look at that. They seem to at first, they seem to get closer and closer together at first, but now they're moving away from each other. What in the world's going on? Now it seems like we're bouncing back and forth between two numbers of about 0.45 or so and 0.84. What in the world's going on? Are those fixed points? Is it two fixed points? Would that make sense? That those would be two fixed points? Think about that for a second. I hope it makes sense that those can't be fixed points. Because when you plug one of them in, you get the other one. They do bounce back and forth, but neither one is a fixed point. In fact, if you use this formula, when mu is 3.4, you'll get 2.4 over 3.4. 24 over 34 is 12/17 for the exact fixed point. And 12/17 is like halfway between 0.45 and 0.84. Not exactly, but 0.706. That's the fixed point. And if you plug that into the 3.4 times the previous answer times 1 minus the previous answer, that does stay fixed, it seems. Although what happens if I make the number slightly off, like make it 0.706, say, and do 0.706, do 3.4 times the previous answer times 1 minus the previous answer. Keep iterating. Now those numbers are moving further away from the fixed point. What in the world does this mean for numerical methods? It means we can run into problems sometimes, is what it means. It's not working. You need to be aware of that in a numerical analysis class, that numerical methods sometimes don't work. Why don't they work sometimes? That's partially what we want to explore today. I'm going to give you a handout here. What we want to do is we now want to try to understand what happened with what are called cobweb plots. We're going to draw the first one together, and then I'll have you work on the second one on your own. So here we have the first example, f of x equals 2.8x times 1 minus x. That's a logistic map with mu equal to 2.8. That's the red graph that you see. And the blue line is, of course, the line y equals x. And I made the axes nice and big and drawn to scale. We have the same scale on both axes, so this makes it as good as possible. Ideally, you have a straight edge when you do this. We want to start with our seed. Of course, you may not have a straight edge. It's okay. P0 is 0.1. We're trying to visualize what's going on here. We're trying to understand what we saw with the calculator visually. This is now no proof of anything. It just is intuitive understanding. So what do? You plug 0.1 into the function f to get the output. Let's go ahead and use the particular numbers again here. It was 2.8 times the previous answer times 1 minus the previous answer. 0.252 was P1. Go up to the red graph here. The second coordinate we're after is slightly bigger than 0.25, which is right there. Yeah, right around here is going to be the point with coordinates P0, P1, 0.1, 0.252. 0.252 is P1, and there I drew a line without using my straight edge. I should have used my straight edge. Want to draw a vertical line there. But then we want to continue the diagram. And a nice way of continuing the diagram here is to not go down here to 0.252 and then go up to the red graph, but to use the line y equals x, in fact. When you're at this point, go horizontally to that line y equals x. Now I'll use my straight edge. Try to make it as horizontal as you can to a point right around here, whose coordinates, since you're on the line y equals x, would be the same. And in fact, it's the second coordinate at this point. Its coordinates are P1, comma P1, 0.252, comma 0.252. Now continue the process. Go up or down to the red graph. In this case, we have to go up. And then left or right to the blue graph. We'll have to go to the right in the next step. In other words, go vertically to the graph of the function, up or down, and go horizontally to the graph of y equals x, left or right, depending on where you are in the diagram. So now we go straight up. Well, let's see what we're going to go to so we can make it as accurate as possible. About 0.53 is what we're after. 0.53 is right around there. I think we're going to go up to right around there or so. With a vertical line. Now we're at the point with coordinates P1, comma P2, approximately 0.252, comma 0.528 if you round to 3 places. Continue. Go to the line y equals x horizontally. That point has coordinates P2, comma P2, approximately 0.528, comma 0.528. Now go vertical. So far, the sequence is monotone, but we are about to violate the monotonicity after this point. The next value is 0.698, so we're after just under 0.7 there, somewhere right around here is where we want to go to. Right around there. Now that point has coordinates P2, comma P3, approximately, this is approximately 0.528, comma 0.698 is what that is. Go horizontal. To this point on the y equals x, that's going to have coordinates P3, comma P3, approximately 0.698, comma 0.698. And now you can see visually in the next step, you got to go down to the graph instead of up. And that's why the next number is smaller. That's why, quote unquote, without being approved. The next number is smaller. And what is it? It turns out to be about 0.590. Just below 0.6, right about here. That's P3, comma P4, about 0.698, comma 0.590, etc. And now if you continue, now I'm not going to bother with labels anymore, and I won't bother with my straight edge. Continue the process. You can see the diagram forces you to head toward the fixed point in an oscillating way. You're forced by the procedure and the nature of the red graph to go closer and closer to the fixed point, back and forth in a non-monotone way. as you keep iterating, the fixed point itself is right there. That's supposed to be purple if you can't quite tell. That's P comma P. And what was the fixed point exactly? It was 9/14. This is 9/14 comma 9/14, which was about, what was it? I forgot. 9/14. About 0.643. 0.643 comma 0.643. Why do we call this a cobweb diagram? I mean, it kind of looks like a staircase here and it looks like a spiral here. Because there are going to be some other examples. We won't see it today, but next Tuesday we'll see other examples where the diagram looks like a crazy cobweb. Depending on the example. Okay. What I'd like you to do for about 5 minutes is turn the page over and do it for the case mu equals 3.4 and see if you can see graphically why it's not approaching the fixed point and instead is bouncing back and forth between two numbers. All right, here's my picture. So again, you start down at the seed, P0 is 0.1. I initially marked it incorrectly. It's right there. Go up to the graph, the red graph, point is coordinates P0, P1. Go to y equals x, coordinates P1, P1. Up to the graph, coordinates P1, P2. We see P2 is about 0.722. That's almost the fixed point. So when you go over to the blue line, I made a mistake here and I made a dot right there and I should not have done that. I want that dot right there on the blue line, y equals x. It's close to the fixed point. But then as you continue the process, you move away. And you get further and further away until you reach sort of some sort of stable situation where you're bouncing back and forth between two numbers that were close to 0.44 and 0.84, I think. Is some sort of two cycle is the official name for it that you end up approaching rather than a fixed point. Is there a way to verify and even find the numbers of the two cycle symbolically? Yes, there is, but we won't do it today. We'll wait for next Tuesday. But the fixed point is no longer attracting, you might say. It's repelling nearby points. What's the condition on why it was attracting when mu was 2.8 and why it's repelling when mu is 3.4? It's related to the slope of the red graph at the fixed point. The derivative. Calculus. This one's steeper there, isn't it? At that fixed point with a negative slope. This one's not as steep with a negative slope. When your slope is less steep, when it's closer to 0, at the fixed point, it's going to be attracting, whether it's a positive or negative slope. If it's steeper, if it's further away from 0, either positively or negatively, it's going to be repelling. It turns out. And in fact, the boundary between close to 0 and far from 0 is a derivative that equals plus or minus 1. 1 unit away from 0 is the boundary between attracting and repelling. In today's Mathematica notebook, that I'm not going to go through completely, that condition is right here. If the absolute value of the derivative of the function you're iterating, g in this case, is less than 1, then the fixed point called x star here is stable. Nearby seeds generate sequences that go toward the fixed point. And on the other hand, if the derivative is bigger than 1 in absolute value, then the fixed point is unstable. Nearby seeds generate sequences that go away from the fixed point. Attracting versus repelling is the same as stable versus unstable. And you can program Mathematica to do a cobweb diagram as well. Here's what a cobweb plot looks like when you iterate the cosine function for any number of iterates you want here. There you get spiraling toward that root or that fixed point that we saw last on Tuesday to be about 0.739. Can I apply it in our current situation? Sure. If I make the function be 2.8 times x times 1 minus x, then we get the first picture. If I make the function be 3.4x times 1 minus x, then I get the second picture. Let's go out more iterations. How about 20 iterations? All right, do you want to see the cobweb? If I make the function be, say 4 times x times 1 minus x. It goes all over the place. Doesn't even converge. That's a sequence, a recursive sequence that's not converging to anything. The numbers bounce all over the place. It's, here's a buzzword, chaos. This has an official mathematical definition. This is chaos theory here. This is mathematical chaos. It is deterministic. The initial condition does completely determine the future conditions, though the number of decimal places to represent that precisely gets bigger and bigger, and so eventually you're always just dealing with approximations. But it acts random, right? You look at that and you're like, those numbers are essentially random. It's like a probability distribution or something. But it's not random, it is deterministic. It's chaotic. We're going to explore this more next Tuesday as well.